For the first 5 seconds, just listen. That sound isn't from a horror movie. It comes from Jupiter. Radio and plasma waves recorded by spacecraft and translated into frequencies our ears can hear. And now, this is Milo. For this mission, we're imagining sending our deep space probe straight toward Jupiter and letting it stay in the planet's environment for 24 hours. Right now, everything looks normal. Power stable, navigation stable, cameras online, radiation shielding nominal. At hour 1, Milo still looks almost untouched, but Jupiter has already started changing it. Not with a storm, not with lightning, not even with pressure. Something invisible is hitting the spacecraft right now, and the closer Milo gets, the worse it becomes. By hour 24, the probe you see here will barely resemble the machine we're looking at now. Some systems will fail. Some damage will be impossible to see until it's too late. And one of Jupiter's most dangerous effects begins long before Milo ever reaches the clouds. So here's the experiment. What actually happens to a spacecraft if we leave it near Jupiter for 1 full day? And before we start, if you want the next Milo mission to go to Saturn, Venus, Neptune, or somewhere even worse, subscribe and tell me where we send it next. Because the first warning has just appeared. Radiation levels are rising, and Milo hasn't even reached Jupiter yet. Before we talk about what's hitting Milo, there's something we need to get straight. Jupiter isn't just a larger version of Earth. It's so much bigger that our brains are actually bad at visualizing it. If Earth were placed beside Jupiter right now, it would look almost insignificant. By volume, you could fit roughly 1,300 Earths inside Jupiter, and its mass is about 318 times Earth's. In fact, Jupiter contains more mass than all the other planets in the solar system combined. Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune. Put them together, Jupiter still wins. And that matters because almost everything terrifying about this planet begins with one thing: gravity. Look at Milo now. That's the exact same spacecraft we saw a minute ago. Nothing about Milo changed. We simply pulled the camera far enough back to show what it's approaching. And somehow, Jupiter is still getting bigger. You've probably heard Jupiter described as a failed star. That's catchy, but it can also give you the wrong idea. Jupiter is overwhelmingly made of hydrogen and helium, like the Sun, but it is nowhere close to massive enough to sustain ordinary hydrogen fusion like a star. It isn't a star that almost switched on. It is something different. A giant planet operating under pressures and conditions that Earth never comes close to experiencing. So the obvious question is, where do we put Milo? If this were Mars, we could choose a landing site. If this were the Moon, we could identify a crater. Maybe we could send Milo through those clouds, find the ground, and see what Jupiter actually looks like from the surface. There's just one problem with that plan. Milo is still thousands of kilometers away from the cloud tops, and its camera has just recorded its first corrupted pixels. The hull looks fine. The solar panels look fine. Nothing has touched the spacecraft. At least, nothing we can see. Because Jupiter doesn't need Milo to enter its atmosphere to start damaging it. The planet is surrounded by an enormous invisible environment filled with trapped high-energy particles, and Milo is flying directly toward it. At hour 1, our spacecraft still looks perfect, but deep inside its electronics, the first damage may already be beginning. And this is where Jupiter's real attack starts. Look closely at Milo. Nothing has crashed into it. There's no storm here, no lightning, no atmosphere pushing against the spacecraft. And from the outside, Milo still looks exactly like it did when the mission began. But those flashes in the camera, those are the first clue. Jupiter is surrounded by an enormous magnetic environment. Inside it, charged particles can become trapped and accelerated to enormous energies. Near the planet, those particles form some of the most punishing radiation belts any spacecraft has ever had to survive. And unlike a rock or a piece of debris, you don't see this coming. That's what makes Jupiter so deceptive. the dangerous environment doesn't begin at the clouds. Jupiter's intense radiation belts extend far into the space surrounding the planet, including beyond the orbit of Europa, hundreds of thousands of kilometers above Jupiter's cloud tops. So, while Milo still appears to be safely approaching Jupiter from space, it has already entered the battlefield. High-energy particles can pass through spacecraft materials and interact with sensors and electronics. Juno has actually used its own cameras to detect this environment. Energetic electron and ion hits can appear in images as dots, streaks, and strange squiggles, almost like static written directly onto the detector, which means that every strange mark appearing in Milo's transmission gives us information. But it also gives us a warning, because the camera isn't the part I'm most worried about. A spacecraft depends on electronics for almost everything: navigation, attitude control, communication, power management, even knowing which direction its antenna should point toward Earth. High-energy radiation can interfere with those systems and gradually damage sensitive electronics. One corrupted camera frame is annoying. A corrupted command inside the wrong computer could end the mission. NASA knew this problem was so serious that when Juno was designed for Jupiter, engineers built something unusual into the spacecraft: a titanium radiation vault. The box protects many of Juno's most sensitive electronic systems. Its walls are about a centimeter thick, and the vault weighs roughly 172 kilograms. NASA estimated that it could reduce the radiation exposure of the electronics inside by about 800 times compared with the environment outside. And shielding wasn't enough. Juno's orbit itself was designed to avoid spending unnecessary time inside the most dangerous radiation regions. Juno tries to minimize the punishment. Our experiment is doing the opposite. We're asking Milo to keep moving inward and to stay. So the radiation dose is going to keep accumulating. And there it is, our first actual system warning. One of Milo's orientation sensors has just returned a bad reading. It recovered, this time. But here's the strange part. Radiation isn't what eventually destroys Milo. For that, we have to go inside Jupiter. At hour 3, Milo is finally close enough for Jupiter to stop looking like a planet and start looking like weather. Those bright bands are clouds, cold, fast-moving layers of ammonia and water suspended in an atmosphere made mostly of hydrogen and helium. And here's the first thing that breaks our instincts. There is no ground waiting underneath them. Jupiter has no discernible solid surface like Earth, Mars, or the Moon. In fact, because there's no physical ground to measure altitude from, planetary scientists use a pressure level of 1 bar, roughly Earth's sea-level atmospheric pressure, as a reference level for Jupiter. So when we tell Milo to descend, we're not telling it to land. We're telling it to fall. At first, the view is spectacular. Bright zones and darker belts stream past in opposite directions. The deeper Milo goes, the more the atmosphere begins to feel less like something you fly through, and more like something you sink into. And those colorful bands aren't just decoration painted across Jupiter's cloud tops. Measurements from Juno revealed that Jupiter's east-west jet streams penetrate roughly 3,000 kilometers beneath the visible atmosphere. Think about that. On Earth, weather feels like something happening above the ground. On Jupiter, the weather itself reaches thousands of kilometers down into the planet. Milo's attitude control system is now working constantly. Small thrusters fire again and again to keep the spacecraft stable and its antenna pointed toward us. Then, the first flash appears. Lightning. Jupiter doesn't just have lightning. Juno has detected unusual shallow electrical discharges associated with high-altitude clouds containing an ammonia water solution, while other Jovian lightning originates much deeper in the atmosphere. And Milo has to keep descending through all of it. Pressure is climbing. Visibility is dropping. The sunlight above is becoming softer, stranger, and increasingly difficult to see. And if this sounds like a mission no spacecraft would ever attempt, something surprisingly close has already happened. In 1995, NASA's Galileo atmospheric probe entered Jupiter for real. It transmitted science data for 58 minutes while falling about 97 miles through the atmosphere. By the time its signal ended, the probe was experiencing around 23 times Earth's sea level pressure, while temperatures had climbed above 300 degrees Fahrenheit. Deeper inside Jupiter, the probe was eventually destroyed, and Galileo never found ground, because there isn't any. On Earth, if you descend through clouds long enough, eventually you come out underneath them. On Jupiter, there is no underneath. The atmosphere simply becomes denser as pressure and temperature rise. Deep enough, hydrogen itself is compressed into liquid states. But Milo isn't that deep yet, because something enormous has just appeared on the horizon. A storm humanity has watched for centuries. Milo turns toward it, and our path is taking us straight toward the Great Red Spot. At hour 6, Milo reaches the edge of the Great Red Spot. From Earth, it looks almost flat, a red oval painted onto Jupiter. Up close, that illusion disappears. This is an anticyclone, a gigantic high-pressure storm trapped between powerful jet streams. Astronomers have continuously tracked the modern Great Red Spot for at least around a century and a half, and even now, it's still large enough to swallow Earth. But something strange has been happening to it. The Great Red Spot is shrinking. Around the time Voyager visited Jupiter in 1979, the storm was roughly twice Earth's size. NASA's Juno mission now describes it as closer to about 1.3 Earths across. And it isn't simply getting smaller in a smooth, predictable way. Hubble watched the storm closely over 90 days and found something researchers hadn't expected. The entire vortex was squeezing in and out, changing its shape while accelerating and slowing. NASA compared its behavior to something almost ridiculous at this scale: a gigantic atmospheric stress ball. Milo is now close enough that the edge of the storm no longer looks like a red circle. It looks like a wall. Winds around the Great Red Spot have been measured at hundreds of miles per hour, with NASA reporting peaks around 400 miles per hour. So we're not going through the center, not yet. We're going to skim the outer edge, and immediately something changes. We're back. But look at Milo. It isn't pointing where it was before. The control system is burning fuel just to recover its orientation. For the first time, Jupiter isn't only attacking Milo's electronics. The environment itself is physically fighting the spacecraft. And here's the part photographs don't show. The Great Red Spot isn't only enormous from side to side, it goes down. Juno's measurements indicate that the storm's roots extend roughly 320 kilometers beneath the visible cloud tops, tens of times deeper than Earth's oceans. What we're seeing from above is only the top of the vortex. And strangely, even its most famous feature is still not completely explained. Scientists have several ideas involving atmospheric chemicals, sunlight, and radiation, but the exact chemistry responsible for the Great Red Spot's color is still unresolved. We've been staring at this storm for generations, and it still won't give us all of its secrets. Milo clears the edge. The signal stabilizes. One attitude control thruster is running hotter than before. Camera noise has increased. Radiation exposure continues accumulating. The spacecraft is still alive, but at hour 6, Milo finally looks like Jupiter has touched it. And if the Great Red Spot were the worst thing waiting for Milo, this would be where we'd turn around.